Hey folks, here we go. Today we get to talk about rockets and impulse, all right? I also have a couple more named problems for us to work on here, so we'll start to see those and start to work through kind of those concepts of how we use those last couple equations we've talked about with impulse, delta P equals F delta T and delta P equals M delta V, all right? So here we go. A 30,000 kilogram rocket containing brave astronauts, you can read there. The astronauts light the engine, which caused the rocket to accelerate from rest to 1,000 meters per second in 5 minutes. We want to know the impulse during the rocket during this 5 minutes. All right. So what we see is we got a couple numbers here that are kind of important for us. Get my pen going here, right? We got 30. That one's not a good color. Let's go here. So we got 30,000 kilograms. We got the word rest. We got 1,000 meters per second, and we got 5 minutes. All right. So once we see this, our impulse is going to be delta P, right? So because we've got time, because we've got velocities, and we've got mass, we have choices here now. We can use either the F delta T, which is tough because we don't have a force. So then we're going to have to default to M delta V. All right. So when we look at this, we're going to see our final minus our initial. So again, that's what it got up to. That's what it started at. That's the mass between the both of them. So what we end up seeing is really this thing on the back end here kind of goes away. All right. So there we've got our 30,000 times 1,000. So we got 30 million kilogram meters per second. Now, if we wanted to figure out the force, guess what we could do? We could take this 5 minutes, turn it into seconds, and then all of a sudden now we got the force that's going to be applied on them. If we were even to look at that, so that's going to be, what is it, 5 times 60, right? So 30, 123 million divided by 300. The force on these brave astronauts is going to be 100,000 newtons, all right? So just another way to look at it. In this case, when we're calculating impulse, that 5 minutes doesn't necessarily mean much to us, okay? All right, so here's what I want you to do. You're going to try these 3 out, all right? So I'll give you a little bit of a pause here, and you're going to run through them, check them out, see how they work, and see if you can answer them, all right? Oh, by the way, 3C, tough one. See if you can get it. It's pretty challenging. All right, so number 1, okay? What we see with number 1 here is that we've got, we've got a force of 35 newtons, we've got a mass of 72,000, and we've got a change in velocity of 0.63 meters per second, all right? So here's the way I like to ask the question, what's the change in momentum caused by the rocket? And then for how long should it be fired? So for us first, A, we want to find delta P. For B then, we want to find our time, okay? So to find delta P, if we know mass and we know a velocity, that's what we're going to use to find our part A, that change in momentum or that impulse, okay? So we're going to take the mass of 72,000 times the 0.63, which is how much speed it changes, or the velocity change for us, and we find this is 45,360 kilogram meters per second, all right? Once we know that then, that is going to translate right into this other impulse, okay? So now what I want you to remember is this is also Newton seconds, okay? Because that's also Newton seconds, that's where this 45,360 can go in there, all right? Once we know that, we know the force is 35 newtons. Divide those two. We see this should happen over 1,296 seconds. So 1,296 divided by 60, that's about 21 minutes, all right? Pretty long time for it to be able to do that, to change its velocity, okay? That was 1. Number 2. All right, a tennis player practices their backswing by hitting it off a backboard, hitting the ball to the board with a speed of 22. It bounces back straight back off the board with a speed of 19. The mass of the ball is 55, and it is contacted with the board for 12.5 milliseconds, or 0.0125 seconds. What is the impulse on the ball? Now, this is kind of a bat and ball problem, all right? And again, when we look at that, we see the speed here and the speed here. Now, if those two are going the exact same direction, great. Then it's a 3 meter per second change, but they're not. This one is going, it bounces straight back from it, whereas this one goes towards the board. So what I did was I just made this second one negative, all right? So I took 22 minus a negative 19, and I got a big 41 meter per second velocity change. All right. I got mass again, I got time again. So again, here I want to find the impulse of the ball. In this case, I'm going to take the mass of the ball, which is 0.055. Remember, grams cannot be. We need to turn it into kilograms here. Okay. So I multiply that by 41. I find that this ball experienced an impulse of 2.26 kilogram meter per second. All right. One more time, just to remind you, this is also Newton seconds, right? Because that's Newton seconds, that allows us to then plug this straight into here. With that, we can take our change in momentum divided by the time of how long it was in contact, and we find that the force here needs to be 180.4 newtons. Okay. Again, just working that first equation. The difference in this one now is that we have a opposite direction. This part right here is absolutely crucial for us. Making sure that that thing is negative because it's going the opposite direction is hugely important for this problem. That's the point where people will start to lose points on us. Okay. All right. Last one. 0.24 kilogram volleyball approaches Tina, and she sets it. Over the period of 0.025, she applies a force of 55 newtons. What is the change in momentum caused by our hands? What is the change in velocity for the volleyball? And then part C, this one's tough. All right. If the volleyball started with a speed of 3.3, what speed did she hit it in the opposite direction? Okay. So we've got a mass of 0.24. We've got a time of contact of 0.025, and we've got a force. All right. So we want to find delta P first. So when we look over here, because we have a force and a time, this works out really nice for us. We can apply our force multiplied by our time, and we get 1.4 Newton seconds. Remember, again, this is also kilogram meter per second. Okay. Once we've got that, then that gets plugged into here. All right, for our delta P, for our change in impulse there. All right, and we take the mass of the volleyball, divide the impulse or the change in momentum by the mass. We find our overall change is 5.73 meters per second. All right. So now what that means is that overall, Tina caused a almost 6 meter per second change. Now, there's two ways to look at this. All right. If this volleyball was going this way, and then she hit it that way, that should make this 3.3 meter per second here bigger. But that's not the case. That's not what's happening here. So this thing went this way, and so she then hit it that way, right? So what happens is we have to have a negative. So one of these two is going the opposite direction. What I did was I said, okay, if this is 3.3, that's my negative because that's going the wrong way, right? Up here, if this was my 3.3, then what would happen is this number here would be a lot bigger, all right? But that's not the case because we said we want this thing in the opposite direction. So I made that negative, as you can see here, right? So I took my 5.73 equals VF minus a negative. Remember, minus a negative means this becomes a positive for us, right? So then we subtract off 3.3 from the 5.73. The final velocity that she hits this with, going the opposite direction, is 2.43 meters per second. Okay? And again, part C there, I'm not going to ask that one on a test. I just wanted to see if you could run that thing and understand kind of the directionality of it for us. Okay? That's what I got for the day for you. Today's another day just to make sure you work through questions. Monday, you'll get a review so that you can practice through some more. Check out homework. Make sure you're working through that. Again, day 2 of trying to get that all accomplished so that next week is a little bit easier for us. All right. Hope you have a great day. Take care. All right. We'll hope to see you soon. All right. Bye-bye.